Very good morning, friends. We were dealing with the side reactions accompanied in the peptide synthesis. We have seen the proton abstract protonation of oxygen or nitrogen, which can occur in the acidic environment, can give rise to byproducts. Similarly, under the basic conditions, proton abstraction can occur, which also gives rise to the byproduct. Today's subject of discussion is side reactions that occur due to abstraction of proton during the synthesis of peptides. If I suppose I take example of glycine, and if I treat glycine in the presence of an base, base as is electron rich, and it can accept the proton. The B minus abstract the hydrogen from the OH of the carboxylic acid. It abstract the proton. When it abstract the proton, the excess electrons are left onto the oxygen to give rise to oxygen anion, which is unstable. The carboxylate anion which is formed. This is to gain its stability. The excess electrons are donated to the adjacent carbon. The carbon has to maintain its tetravalency. That's a bond between this carbon and this carbon breaks, and it gives rise to an carbon ion and carbon dioxide. Abstraction of acidic proton by base of from carboxylic group gives carboxylate ion, and it forms the formation of another ionic ester at alpha carbon. And as these do not have carboxylic acid group, the peptide bond formation is arrested. Thus, this kind of side reaction can occur under basic condition. Hence, while using the basic condition, we have to optimize for preventing this type of reaction. Instead, means we should use a comparably weaker base. Strongly basic condition should not be used. This side proton abstraction can also give rise to racemization to give the racemic mixture to via formation of succinic acid derivative. If I take aspartyl acid containing peptide, here this is the aspartic acid which is having the peptide bond with another amino acids which is mentioned, not shown over here. In the presence of the base, in the first case we have seen the proton abstraction took place from oxygen, but here the proton abstraction takes place from the nitrogen over here, giving rise to nitrogen anion. This it is electron rich, and adjacent to it there is the carboxylic carbonyl group, which is a site of electron deficiency due to the presence of electron withdrawing group adjacent to it. This is electron rich and deficient. Unlike pulse attractor, it forms the bond and OH gets kicked off, and it gives rise to succinimide, a succinic acid derivative. This succinimide, which is formed, loses its the property of enantiomerism. It gives rise to racemic mixture when we hydrolyze this and open up the ring system. This racemize formation of succinimide occurs when the peptide chain has an amide bond and there should be a free carboxylic acid group. The nitrogen, which is electron rich, which can act as a nucleophile and it cyclizes, and that's why you get succinimide. This affects the stereochemistry of the peptides. Similarly, if I take benzoyl aspartyl glycine, we have seen aspartic acid in which the is protected by benzoyl group. The base subtract the proton, giving rise to electron rich nitrogen, which attacks on the carbonyl carbon which is adjacent to it, and this bond breaks away to give benzyl alcohol and succinimide. Similar reaction can also occur. Similar derivative is also formed during strongly acidic condition also. The same benzoyl aspartyl glycine, if I take under acidic environment, this as an electrophile. In the presence of an electrophile, there is an electromeric effect across the carbon-oxygen double bond. That's why pi electrons moves towards oxygen, creating rise to a carbon, the oxygen anion, and here as the electrons have moved a carbocation. This O minus combines with H plus and a carbocation is formed. This amine having the nitrogen has lone pair of electrons. This is electron rich and this is electron deficient and they are adjacent to each other. It attacks on the positive center to satisfy the electron deficiency, but carbon has to maintain its tetravalency. That's why the carbon oxygen bond breaks and benzyl alcohol gets kicked out, and I'll get the corresponding succinimide derivative. Succinimide. The same succinimide is found by protonation also and by proton abstraction also. The proton abstraction can lead to racemization by forming azolactone as an intermediate. This occurs in glycylalanine. The glycylalanine can exist in enol form. The keto form gets converted to enol form. The nitrogen hydrogen bond breaks, that electrons form bond with the adjacent carbon. The pi electrons moves on to the oxygen. The H plus combines with O minus and gets the enol form. Enol form of glycylalanine, which gives OH. In the presence of the base, the proton abstraction occurs, give rise to oxygen anion. This oxygen anion, which is nearer to the carbonyl carbon present in the carboxy ester group, attacks on it, and X minus X moves away and forms azolactone ring system. Keto group undergoes ketoanionyl tautomerism to give the enol form. The enol OH is abstracted by the base, giving rise to oxygen anion. This has a positive center because carb X is a easy leaving group and then it is prone to cyclization and forms as a lactone ring system. This azalactone ring system which is formed is resonance stabilized. In the presence of the base, due to it has an acidic carbon at its flank between carbonyl and nitrogen, two electron withdrawing groups. In the presence of the base, this hydrogen gets abstracted, giving rise to the carbon ion, and this is resonance stabilized by the adjacent carbonyl group. And again O minus form double bond, shifting the pi electrons to the next position, and this gets shifted to the next position, and minus combines with H plus, it gets H over here. This is resonance stabilized. That's why racemization is easier. Racemization occurs through these isolactones rather than direct abstraction. Various factors influence the azalactone formation. The factors that affects the azalactone formation and its racemization is the nature of amino acid involved and the solvent which we use for the reaction and the presence of a tertiary amine. Phenyl azalactone is more stable than tertiary azalactone, is more stable than primary, is more stable than second, then methyl azalactone respectively. The electron withdrawing effects are present in the acyl groups increases the stability of the anion, and proton abstraction can be facilitated. These are the factors, and this azalactones, when it is hydrolyzed, it gives a racemic mixture, which is having a stereochemistry of desired and undesired nature. Proton abstraction can be mediated through carboxydiamides in tyrosine. Carbodiamide, it has the lone pair of electrons. It abstracts the proton from the OH attached to the phenyl ring system, giving rise to oxygen anion, and this can get acylated to give O-acyl derivative, to give acyl tyrosine. This can occur also in the presence of a base instead of carbodiamide also. Here carbodiamide acts as a base, or it can occur in the presence of triethylamine or diisopropylethylamine or other bases. That's why when this has the functional group, this should be protected such that this reaction do not occur. The phenolates are the alcoholates formed by proton abstraction to give alkoxide anion, and this gets acylated to give acyl tyrosine. These are all the side reactions that can occur by proton abstraction. In the next presentation, we will deal with other side reactions of these peptide syntheses. Till then, have a nice day. Thank you.